Daily Q done. You haven't already.
Chef, are you coming to attention?
I can't. I have to teach a class next hour.
Bring them all.
Yeah, bring them.
I don't think I'm
No,
allowed
no.
to.
They can
They're all seniors.
Okay, that's fine.
Some of them will be there anyway.
Yesterday, Anna said she was gonna up all of us and show up.
Are they live streaming on our website?
They sent us like a link.
You want the link?
Someone email me the link.
I'll share it.
I'll make my seniors watch it.
I'm sure they'd be okay with it instead of doing the actual work.
Oh, they'll still have to do work. It'll just play while we do work.
She's like, I'm gonna show up and call.
Everyone should be forced to watch this.
She's like, everybody better say goodbye.
All right, we have the remainder of chapter 16 to get through today. When we are done with that, I will not give you homework, but we will be finishing up just some topics within chapter 16 tomorrow during class, as well as likely doing a lab, just so you are prepared for what's going to happen tomorrow. So please do come in lab appropriate clothing. Obviously today wouldn't have been a great day to do lab, but closed-toed shoes, I will remind you, I know it's getting nicer outside. Closed-toed shoes. If you have long hair, please make sure you have something to pull it back with. Just kind of a quick reminder that it is getting nice, and I am aware that our wardrobes tend to suffer as a result. The last few topics within our chapter all kind of build on what we've already talked about with acids and bases and how they behave. We've seen the reaction before of an acid that donates its proton to water and kind of creates this dihydronium ion as well as the conjugate base of whatever your acid was. The next thing we want to talk about is how are ions, cations, and anions affected? And the answer is very similarly. And so up here we see a reaction that forms our hydroxide as well as our conjugate acid. You've seen this reaction before. In the past we called this our Kb equation, right? So we had some kind of a base that we started with. We added it to water. The water acts as our acid, removes the proton, and creates our hydroxide ion and our conjugate acid of the base we started with. From there, we want to talk about how those cations, which aren't necessarily classified as bases, okay? Those cations can act and how they are impacted in different types of scenarios. Cations that have protons on them are going to act like acids, of course, and they're going to end up lowering pH, right? So remember that acids lower pH, bases raise pH. Okay, so cations that we add to a solution that are positively charged, is the definition of a cation, are going to lower the pH of a solution because in this particular case, they act like an acid, right? They have that extra proton to donate, so they're going to do that. Yes, ma'am?
Does that mean
Anions act like bases. That's what this was saying. Anions are going to act like bases. They're going to do the opposite. They're going to raise pH.
Can you go back one slide for a second?
Sure. You do have access to this as well. Just don't forget that. It is up on Canvas as usual. So if you missed something or you have, hey, I didn't get the last part of that sentence, all of that stuff is up on Canvas for you. So anions act like bases, cations act like acids if they have a proton. Remember, that is one of the requirements. They have to have that extra proton to donate. And those will affect pH as we've discussed. Okay? Other things to think about is the fact that we've defined so far a base as something that can accept a proton. And what we're looking for in that particular case is what we call lone pairs of electrons, or non-bonding electrons, as your book likes to call them. Those non-bonding electrons on oxygen are locations for protons to attach. So don't forget that particular thing. Just like we talked about NH3 being a base, that's ammonia, likes to attach to a proton and become NH4, which is what we saw on the previous slide, NH4 has gained that proton somewhere, and in reality, that proton attached to its center atom at the lone pair of electrons that was available. So we have to kind of adjust our definition of acid and base. And we do this towards the end of this chapter because up until now, the proton movement thing has been a very good approximation of how most acids that exist behave. Most acids that exist, we will say, are proton donors, and most bases that exist are going to be proton acceptors. The Lewis definition, Lewis also being the same Lewis as Lewis structures, is slightly altered to include all chemical species. So it doesn't have to have a proton in order to be an acid. It doesn't have to have a lone pair of electrons, or doesn't have to be a proton acceptor to be a base. Okay? Like I said, gets a little bit more complicated. Before we get there, we are going to talk a little bit more about our metals. So the size of our metal impacts how acidic the metal can act. And so what we say then would be the larger the cation, aka the larger the charge on the cation, the more acidic it's going to be able to make a solution, right? Because the more positive charges it has, the more ability it's going to have to donate protons and so on and so forth if it's attached to protons. So think the difference between a diprotic acid, 2 protons, and a monoprotic acid. One has a lot of protons and one only has 1. Okay, similar idea to our cation charges. The higher the cation charge, the smaller they are, which means the more acidic they can behave in solution. And we see that with that Ka. Remember that Ka values are indications of strength. pHs are not indications of strengths. pHs are very easy to misinterpret. We use them as an approximation, but Kas are very good numbers to use to identify how strong an acid is. Remember, the smaller the exponent, the stronger that acid is going to be. All right. That brings us to the effects of our cations and anions on our acid pHs, on our acid-base chemistry, etc., etc. There are a total of 6 of these. The first 3 all talk about how an anion that is the conjugate base of a strong acid, okay, think strong acids, there were 7 that we've talked about, is not going to affect pH. Because remember that a strong acid is a strong acid by definition, completely dissociates. Okay, you're going to have to do a lot in order to get something to happen to the pH of a strong acid. And adding an anion is not going to help. It's not going to change the pH of the solution. All right, our next rule is that if the anion is the conjugate base of a weaker acid, it will increase the pH, meaning our pH will become higher, right? So that weak acid is going to have a higher pH. If you add more of the conjugate base of that weak acid, you're also going to impact that pH by raising it up. The next is going to be that the cation that is a conjugate acid of a weak base is going to lower pH. Conjugate acid of a weak base lowers pH. And this is if you add the thing at the beginning, right? So if you add a cation that is the conjugate acid of the weak base in your solution, then you are going to lower pH. And this is all based on Le Chatelier from last chapter. All you're doing is manipulating equilibrium. And what we're talking about here is how that equilibrium shifts and then affects pH. Because remember, pH is measured using that concentration of the hydrogen ion on whatever side of the equation you're discussing. Next is going to be cations of the Arrhenius bases are not going to affect pH at all. Cations of our Arrhenius bases are not going to affect the pH at all. So what is an Arrhenius base? Anyone remember? Way back when. Arrhenius acids and bases were defined by the presence of the thing they produce. In other words, an acid was defined as something that would increase the concentration of your hydrogen ions, and a base is going to be defined as something that would increase the concentration of hydroxide ions. So the cations of the Arrhenius bases will not affect pH. Okay? Adding another metal that doesn't have anything to do with your acid or base will lower pH. Remember that those metals are positively charged for the most part. When they are positively charged, they can attract negative things, which means they're going to be removing hydroxide, which means they would be lowering our pHs. When a solution is going to have both a weak acid and a weak base, our pH is going to completely depend on Ka and Kb. So in that case, we have to do the math behind it. So if we have a weak acid that we added to a weak base, we have some equilibrium chemistry we have to do using our Kas and Kbs. Okay, so some of the things that we can talk about that affect how strong an acid is. Remember, this is the Ka value. Things that affect how strong we consider an acid. One of the things is going to be the polarity of the bond. Hopefully that doesn't shock you. The easier it is to pull off the proton, right, the more acidic the thing is going to be. So the more polar the bond, the more acidic the compound's going to be. Remember, polar is the indication of which one hogs the electron density. If your thing is very polar, that proton doesn't have electron density, easier to remove. Easier to remove means more acidic, okay? Because the protons are going to be easier, or as far as leaving the compound, not as much resistance. As we move from left to right across the periodic table, really only the non-metals on the periodic table. Think CH, NH, OH, FH, those types of bonds. As we move left to right, we're going to see acidity go up. That's why HF is one of our strong acids, right? HCl is one of those strong acids. As we move top to bottom, same idea. The bond gets more polar when it's attached to water, etc. Remember those periodic trends from way back when. Another factor is going to be the presence of OH bonded to some other atom. If that other atom is super electronegative, remember that the same idea is present, right? So if we say that a bond between a hydrogen and something has to be very polar, the bond between an OH and something, if that is also very polar, we're going to see the same idea, more acidic, the acid. These are oxyacids. The OH is not the thing that's being removed, it's the H attached to the O that is being removed in this case. Hopefully it does not shock you that the more oxygen something has, the more acidity can increase. More oxygens means more opportunity for protons, which means more locations for protons to be removed if they are present, which means more acidic. So as the number of oxygens increases in an acid, the acidic proton is more and more acidic by definition. And the last factor affecting strength is resonance. An obscure term from way back when we were talking about Lewis structures, which is of course our next topic. But remember that resonance is the movement of electrons from one bond to another based on where they are currently located. Remember that these two types of structures are essentially equal in our mind. The resonance concept from last semester is one that still applies. And this resonance idea has an effect on how strong an acid can be. the base becomes more stable, which makes the base easier to manipulate and makes the conjugate acid more acidic. Resonance makes something more acidic. Remember that our resonance idea usually only occurs in oxygens and carbons? Like this is a pretty typical type of resonance. We've also seen it with nitrogens. I think we've seen it on, I want to say, sulfurs and phosphorus atoms. But for the most part, carbon-oxygen bond is a typical, call this an acidic group in organic chemistry. Our last few definitions of acid and base change things a little bit. Lewis acids now become electron pair acceptors, and Lewis bases now become electron pair donors. So instead of saying removing a proton, we can talk more generally about a feature that is present in a lot of different compounds, lone pairs. So up here on our example, we have a Lewis acid, which has an opening, if you will, for a pair of electrons, and we have a Lewis base that has a pair of electrons to donate. In this donation, what happens is we form a bond. This is our all-encompassing definition of acids and bases. You now have 3 at your disposal. We have the Arrhenius acid and base, which was introduced as a proton increase or a hydroxide group increase. We have the Bronsted-Lowry, which is our most common, proton donor, proton acceptor. The most common that I need you to know, Bronsted-Lowry. And now we have our third, which is our Lewis acids and bases, which now can include a huge array of substances. So just to reiterate, Lewis bases, electron pair donors. Now something to know in comparing Bronsted-Lowry to Lewis is that if you have a Bronsted-Lowry base, it's also going to be a Lewis base. The difference between Lewis and Bronsted-Lowry bases is that our Lewis bases do not have to interact with protons. They can interact with anything else. They can interact with other lone pairs. Yes, sir. Yes, you may. We are done. Ta-da! Stop. So I do want to remind you, things have been due in the last few days. You have the 16.67 that we finished up yesterday. If you have not submitted it, you need to submit it. Okay? You have a very close, aka end of the week, end of the quarter, which means daily cues and labs that are in your lab notebook must be done. Spend the time in class going back and at least identifying if there are labs you need to finish up. Remember to pay particular attention to those conclusions. I care about them. We talked about them at the beginning of this semester for a reason. Okay, so spend some time going back into your labs for the remainder of class. You have plenty of time. And looking at what you need to do in order to complete your labs, your daily cues, and if you have anything missing, get it submitted. Okay, your grades are due Monday at noon. Yes. Is it still showing missing? Yeah. Yep, I'll take care of it. Yes, ma'am. Sure. The one for today?
Yes.
Okay.
So recently that one